To construct confidence intervals for variance and standard deviation, a different statistical distribution is needed, and it's called the chi-squared distribution. The symbol for chi-square is this x-looking character raised to the 2, and it is the Greek letter chi. The chi-square distribution is similar to the t-distribution in that it is a family of curves based on the degrees of freedom. Here's an example of a chi-square distribution with 1 degree of freedom. Here's one with 4 degrees of freedom, one with 10 degrees of freedom, and here's one with 15 degrees of freedom. A couple of characteristics about the chi-square distribution. All chi-square values are greater than or equal to 0. The area under each distribution curve is equal to 1 or 100%. The chi-square distributions are positively skewed, so the distribution is not symmetric. The degrees of freedom are equal to n-1, or the sample size minus 1, and as the degrees of freedom increase, the chi-square distribution approaches a normal distribution. As far as the 90%, 95%, and 99% confidence intervals, they have a similar concept for the chi-square distribution. However, since the chi-square distribution is not symmetric, the critical values will not be equal to each other. So let's say that this is a chi-square distribution with 20 degrees of freedom, and we want to construct a 90% confidence interval with a sample size of 22. So 90% of the area under the curve lies between these two values, which I've marked with red lines. And these lines, which represent the critical values, are noted as chi-square left and chi-square right. And since 90% of the area lies between the lines, 10% lies outside of the lines. So we have 5% under the curve to the left of chi-square left, and 5% under the curve to the right of chi-square right. Now we need to use a chi-square distribution table to find these critical values. This table is based on the degrees of freedom and an area or percentage to the right of a chi-square value. So to find the value of chi-square left, we need to know the total area to the right of that value. And in our graph, we have 5% to the left. So 100% minus 5% gives us a total area of 95% to the right of the value. Since our sample size is 22, n-1, 22 minus 1 equals 21 for the degrees of freedom. So in the table, we want to find the 95% or 0.95 column here near the top. And under the degrees of freedom column, we go down to the 21 row. And the value listed where these intersect is 11.591. And that is our value for chi-square left. Next, for chi-square right, again we need to know the area or percentage to the right of chi-square right. And we already know that from earlier. It's 5% or 0.05. And again, the degrees of freedom is 21. In the table, we find the 0.05 column near the top. And under the degrees of freedom column, we go down to the 21 row. And the value listed where these intersect is 32.671. And that is our value for chi-square right. Now that we have an understanding of how to use the chi-square distribution table, we can construct confidence intervals for the population variance and standard deviation. And there are two assumptions for constructing these intervals. The sample must be a random sample, and the population must be normally distributed. The formula for the confidence interval for a variance is n-1 times s squared divided by chi-square right less than sigma squared less than n-1 times s squared divided by chi-square left. And the formula for the confidence interval for a standard deviation is square root of the quantity n-1 times s squared divided by chi-square right less than sigma less than the square root of the quantity n-1 times s squared divided by chi-square left. And the degrees of freedom is equal to n-1 for both of these. Alright, let's unpack these formulas. In both of these formulas, n is the sample size, s squared is the sample variance, or you could look at it as s is the sample standard deviation. Chi-square right and left are critical values determined by the confidence level and the degrees of freedom. And sigma squared is the population variance, and sigma is the population standard deviation. Okay, example time. Let's say that a protein powder manufacturer randomly selects and weighs 25 samples of its top-selling product. The sample standard deviation is 4.8 grams. Assuming the weights are normally distributed, construct 95% confidence intervals for the population variance and standard deviation. Let's start with the variance confidence interval. To use our formula, we need to know 4 things. N, the sample size, which was given 25 samples, S, the sample standard deviation, which was given 4.8 grams, and chi-square left and right. So we need to find chi-square left and right. We're using a 95% confidence interval, and the degrees of freedom are n-1, 25 minus 1, so 24 degrees of freedom. Here's an example of a chi-square curve with 24 degrees of freedom. In this middle section we have 95%, our confidence interval. These two red lines are our critical values, chi-square left and chi-square right, and we have 2.5% outside each of these lines. Now to the chi-square distribution table. For chi-square left, we need to know the total area to the right of that value. And in our graph, we have 2.5% to the left, so 100% minus 2.5% gives us a total area of 97.5%, or 0.975, to the right of the value. So in the table, we want to find the 97.5%, or 0.975 column here near the top. And under the degrees of freedom column, we go down to the 24 row. And the value listed where these intersect is 12.401, and that's our value for chi-square left. Now for chi-square right, we need to know the area or percentage to the right of chi-square right. In our graph, we have 2.5%, or 0.025 to the right. So in the table, we want to find the 2.5%, or 0.025 column here near the top. And under the degrees of freedom column, we go down to the 24 row. And the value listed where these intersect is 39.364, and that's our value for chi-square right. Now we can plug and calculate into the variance formula. So we have 25 minus 1 times 4.8 squared divided by 39.364 less than sigma squared less than 25 minus 1 times 4.8 squared divided by 12.401. And our final result is 14.05 less than sigma squared less than 44.59. So we can be 95% confident that the true variance for the protein powder is between 14.05 and 44.59 based on a sample of 25. To find the confidence interval for the standard deviation, we could use the formula, but the formula is actually the same as the variance formula, but taking the square root of both sides. So we can just take the square root of both sides of our answer from finding the interval for variance. Square root of 14.05 and square root of 44.59, which gives us 3.75 less than sigma less than 6.68. Alright my friends, that be the basics on finding the confidence intervals for the variance and standard deviation. Hopefully you got something out of this video. I do have more videos right there for you. Till next time, I am out of here.